a major player in the in-memory compute space. I'm here to really sort of rationalize or convince people that combining in-memory compute technology with Cassandra actually makes sense for certain use cases. It's, obviously it's under the sort of the banner of extremely high performance, low latency, and that means different things to different people. I've seen various talks defining real-time in various ways. We're talking pretty much short of having a real-time operating system is like the most realist real-time you can have. Apart from the general topic of in-memory compute with Cassandra, I'm also going to dig in a little bit into Storm, how that plays with Cassandra, how our product XAP plays with Cassandra, and then how all three of them can actually combine to go to even more extreme levels of performance than Cassandra along with Storm alone. So let's get started. I feel like I got like a half an hour, so we'll plow on. So this is just a quote from Ed Dumhill, just saying that the sort of the next generation of big data is dealing with real time, and we've seen that as a common thread through a lot of the discussions here. How do we actually get real time or near real time? Again, there comes that ambiguous definition. And in the same way that Hadoop has been born out of large-scale web processing, well, there's different aspects to real-time and big data in the context of real-time processing. There's velocity and volume. So, we're very familiar with Cassandra's actually handling both of these pretty well. Matter of fact, our integration with Cassandra was based to a large degree on the fact that it had extremely high write performance, which makes it a perfect sort of companion to in-memory technology, because by definition, the amount of data you're going to be storing in memory is not going to be the same as you're storing on disk in a large distributed system. So you need a very fast write speed in order to keep up so that the real-time in-memory component doesn't fill up with data and therefore either cause your clients to be denied or something even worse occurring. So for the most part, we're not talking about volume here, although our product does create a large amount of, hold a large amount of real-time data in memory. But we're talking volume, of course, on the Cassandra scale here, which is way beyond what you'll put into memory. So the main focus is velocity. And what does that mean? This slide is just meant to communicate the different aspects of why you might need real-time processing. Real-time in the sense of now, real-time in the sense of real-time events, not just polling a table or running pretty performant queries against a static data set, but how can I be notified when certain things happen? How can I do real-time aggregations, real-time counts, and so forth? And of course, all these come up. All these companies use in-memory compute in order to enhance their performance. So I think we can break down big data analytics, which is what I'm going to be calling the aggregations, the counts, and so forth. So let's just call them analytics. So you can break them down roughly into counting, correlating, and research. And each of these actually maps to a different level of real time, typically in going left to right in a decreasing order of real time. For example, let's take Twitter example. If I'm going to use a counting example at Twitter, I'm going to be counting how many signups, how many tweets, how many retweets, perhaps average latencies, maybe I'm aggregating information by country, city, gender. It doesn't really matter, but the point is that it's probably not terribly computationally expensive, and it needs to happen instantaneously. The data is in flight, typically to another system, to Cassandra, to a system that's doing long-term storage, doing vast accumulation of data. So you don't have a lot of time for processing. Correlating, what devices fail at the same time, what features gets users hooked. These are higher level questions. So now you're, rather than just asking what, you're starting to ask why, and correlating different events, probably different aggregations against each other across time. This takes more time. This is something that's typically not happening at the scale that I'm addressing here. And then the final level is research, and this would equate roughly to a Hadoop job. So we're talking about something that could take many minutes to complete. Data science, sentimental analysis, trending, different patterns in data, so forth, research type work. So I'm going to be talking about only in the real-time mode here, meaning less than a few seconds, certainly less than a few microseconds or milliseconds anyway. Reasonably quick would be seconds to minutes, and then batch hours to days. You might compress these a little bit. I'm not sure that's everybody's exact definition of that, but let's just go with that. So again, for the lowest possible latencies, you're talking about event-driven stream processing. By definition, you don't have time to pull a static data source or even a static data source living in memory. And it's extremely high resolution. So we're counting every tweet, and we'll get into what that means as we go forward here. Ad hoc querying, this would be a typical application of a Cassandra type, a big data, NoSQL database, doing ad hoc querying, more like conventional database type operations. And then of course, the long running batch jobs, extract, transfer, load, map, reduce, and low resolution. Now you're kind of zooming out from the data and you're finding patterns and trends and so forth. And that's what we're here to discuss, of course. That's no secret, I imagine, to anybody. Okay, so really the approach we've taken, what we're taking actively with current clients and so forth, is the mixture of velocity and vast volume. So a lot of V's. But to produce the result where you want to get everything together, a very nice approach is combining in-memory technology and big data. So I'll be talking about data grids and storm and how they mix and match and can be used. So first, the concepts behind an in-memory data grid. The data grid is essentially treats RAM as a disk. It treats RAM as though it were persistent. And it creates that illusion by partitioning data across a cluster where, for example, this thing doesn't have a pointer in it, does it? Each memory has, every item in memory has a replica, at least one replica on another node in the cluster. So on writes, you typically suffer a short network hop where you're in a serialization cost, but still the latencies for writes are typically in the low hundreds of microsecond ranges, and the latency for reads are in the low tens of microsecond range. So the data is partitioned across a cluster. This is not in the same sense that a NoSQL cluster is partitioned. We're not talking about eventually consistent storage here. It's more akin to an in-memory database to a certain extent that, I mean, you could view it as an in-memory distributed object-oriented database. So when you write to it, typically the backups are made synchronously, so there's no chance of a split brain or an inconsistent view of data. And like a database, they'll operate transactionally in memory. So they're highly available. Typically the grids And a grid computing system like ours is actively managed by management processes and agents that are running on the nodes with the containers for memory, so they're tolerant of failure. The system notices failures of components, restarts them as needed, so that the client gets a continuous view of what amounts to a large memory space, far larger than a single node can hold, up into the terabyte ranges, not hundreds or thousands of terabytes like Cassandra, but low terabytes. And the other key, especially for the event processing and the real-time processing, is that code is co-located with data. So this is an idea. It's an old idea, but certainly if you're familiar with Hadoop, Hadoop's concept of actually moving the code out to the data, the mappers go out to the data to do the local processing on each node in the system. There's a similar concept, at least in XAP, where you can deploy code to it. The code is resident in memory with each partition of the data, and therefore the event latencies in memory are extremely short. So that's where you get these microsecond level delays. Now, if you put Data Grid and Cassandra, or XAP, being a GigaSpaces employee, together with Cassandra, you really get a complete solution, provided that your Data Grid supports persistence, which seems like a conflict in terms based on what I was just talking about. But the way the grid can be set up, and is typically set up, is that it does asynchronous write behind. For all changes in the grid, will actually, on a per type basis, will be asynchronously written to the underlying Cassandra data grid. So to put in an event processing flow with this system, data flows in to the in-memory cluster. The processing, essentially the data is resident in memory long enough to produce side effects. Side effects being counts or aggregations or any other short-term, and it really varies. I mean, the amount of time you have to do the computation is a function of how fast the data flow is coming through your system. If you're doing, millions of messages a second on a single node, then you're going to have to be not doing much in your aggregator, but you could do, much more in-depth processing. Side effects are calculated, and since they're calculated in memory in the grid, they're persisted in the grid. And if you recall, the grid is akin to an in-memory, it's an in-memory persistence. So the data lives there, it's highly available, it's reliable, you can query it from the outside, in real time. You can also throw off events to listeners, arbitrary listeners, since the data is in memory. Arbitrary listeners can be attached to the data for updates, so that you can have dashboards or any other sort of external system being notified asynchronously with the process. So, and I think that covers pretty much everything there. Okay, let's move on. So I guess just to clarify that, events come in. And the event, if we take, say, a click stream as an example of an event, something perhaps coming from a web log, a Flume's output, something like this, flows into the in-memory grid. Each one of these events only exists in order to aggregate data. So the aggregator is the goal. Once the event has been processed, the data is evicted, but simultaneously is asynchronously replicated to Cassandra for doing the normal Cassandra type queries you might want to do, that you don't need real-time event processing, you don't need, perhaps you don't require that level of performance for. Another possible use of this is, of course, that event queue as it's flowing through the in-memory grid can be modified. So you could filter it, you could mutate it in some way, you could have some other data in the grid itself doing enrichment of these events prior to them even getting to Cassandra. So you could have some kind of reference data. You could have events flowing, say, from a customer, for an example, and have your database of customers residing in the grid and the stream flying past it. Every time an event hits it, you go out, run a query on that customer table, enrich the data, and then it gets written automatically asynchronously to Cassandra in the background. And so I just want to rip through this. Just some technical details for us. In our case, our Cassandra interface, we have a Hector and a SQL-based interface. We use SQL for the read side, and this is really not a topic for this particular, or a discussion for this topic, because we're talking mainly on a write basis, but we also can sit in front of Cassandra and do read-through type caching, in which case we use SQL in order to pass queries through to the underlying Cassandra engine. The in-memory data must, of course, be mapped to column families in some way, or maybe not, of course, but that's the way we do it. So our data is stored in memory as object-oriented, so what we do is have a transformation occurs. By default, we would use something like a class name. We have to provide the column family mapping, for maybe just convenience, but also because there's a limitation on the length of column family names, and you might have to do some modification there. We have a default one, but that's okay. You must serialize individual fields, so if you have nested objects in memory, which may or may not occur in a situation like this, but we provide the ability to do object model flattening. If you don't provide your own serializers, then you wind up with essentially Java serialization in byte fields in Cassandra, and you won't be able to search on those fields. The object model flattening, though, if you look at the example here, if we have a class here that has a nested subclass, which is represented below it, when it gets written to Cassandra, it'll actually create a column family dynamically based on the type, and it'll represent the class, for example, the subclass with a dot notation. And that way you can introduce indexes that span both the grid and the database, but that doesn't apply to real-time event processing so much. Okay, so what are the virtues and limitations? Because we're going to get to Storm here. It's nice because it's a complete stack. Like I said, it's got the real-time persistence, the super low latency, and so forth. And it also gives you transactions and all this good stuff, and it sits on top of Cassandra. It's elastic and so forth, but it could be faster, okay? High availability is not free. I discussed that already. An in-memory data grid like this will never be able to compete performance-wise with Storm in terms of raw numbers. As far as in-memory processing, there's no way for that to occur because Storm does not bear the cost of persistence. It pushes persistence out to the edges, essentially, outside of the model. So if you need to go faster, you might need to go to Storm for the event processing. Complex event flows are not easy to assemble or understand. What we talk about here, I talk about individual event processors. There's no facility, we'll dive into Storm really briefly, but there's no facility for setting up any kind of a flow without connecting together different event processors inside of XAP. So if you go to Storm, Storm does give you those things. It's a popular open source real-time in-memory streaming computation platform. It has a distributed runtime and an intuitive API. So it runs on a cluster similar to an in-memory data grid, but it's quite different. It doesn't focus on storage. It's only focusing on moving data through as fast as possible and transforming it. It's also scalable and fault tolerant, but in a totally different way. It was developed at Backtype, open source by Twitter, and I recommend if you're interested in it, definitely go check out stormproject.net because it's a fascinating project. It's got the concept of streams. So these are abstractions built on actual streaming model, which is absent from a generic in-memory data grid processing system. So it's got concept of a stream, which you define, which is an unbounded sequence of tuples. So it's a simple data model. Spouts, which are essentially the sources of queues, and then bolts, which are where the actual work is done, if there's any kind of aggregations being produced. Filters, joins, aggregations. And then there's topologies, and all the topologies are a container for these things. You create workflows based on these concepts, putting them together. And here's an example of a topology that's been put together. You see a spout. There's a, in this case, it says Zap Trident spout, which I'll get to, but that's sort of selling my own spout, which connects to XAP. But and you notice how it connects. If you're familiar with cascading, it has a similar type API, but it uses a builder type interface in order to connect together the different steps in really a stream processing workflow. So it's not just getting an event and counting it or something. It's actually routing data through to through various processing steps. And each one of these will create a bolt behind the scenes, and it's kind of hidden from you. And you can give it parallelism hints to tell how much you want to fan out processing on a certain level, depending on the computational cost of it and so forth. And then you just submit it. It's got like I said earlier, it delegates persistence to external providers. It assumes that the source of tuples can replay them. I mean, for the most part. You can't have unreliable sources of tuples, but by and large, for the maximum performance, it has to be able to replay tuples. And Cassandra, if we take Cassandra as an example of a persistence, imagine you're doing an aggregation. And before I talked about doing an aggregation in memory. If you have a bolt that is aggregating the stream as it's flowing past, it has to write somewhere if you want to persist it. So that's going to go to a data store, to Cassandra. Cassandra is a common partner because of the write speed to Storm. So it's a good match for it. So Storm, this is just to point out some of the differences. Storm is optimistic processing, is what I'm calling it, but as opposed to a data grid, which is really pessimistic. So Storm assumes that tuples in flight are going to succeed and reach their end state, and their end state is defined as all the bolts have successfully processed that tuple. If there's any kind of a failure, it doesn't restart in the middle or something. It doesn't maintain a state in that sense. It will command the spout to re-emit the tuples. So to get high performance, so that alone, since it's not attempting to persist, continuously, that speeds it up and streamlines it. It uses batching and pipelining for performance. So the highest performing spouts will emit batches of tuples together, and multiple batches can be in flight simultaneously through the system. And if one of them fails, then the spout has to be able to replay it, which means the spout has to, of course, persist if you want a highly available system. Any kind of quasi-queue-like data source can be fashioned into a spout. It really doesn't matter. If you really want sort of a low feature type spout, you can connect to something that can't even replay tuples. It just will mean that if you have a failure, you just lose the data. No persistence is ever required inherently by Storm, so that's why it's so fast, why it can process at such a high rate. And this is just an example of a flow. So if you are, in the case, aggregating to Cassandra, you might have some portion, maybe the first bolt there is doing a split, the second one is doing some kind of a count, some kind of aggregation like that, and then it writes its results into Cassandra. Okay. So that's really fast. It's going to go as fast, it's certainly going to go as fast as Cassandra can go. It'll go as fast as you want it to go. But if you want it to go faster, you need to eliminate the non-memory components. So when you start thinking of RAM as a persistence medium, then when you see something like any kind of a architecture that actually winds up writing to disk, you start thinking, oh, I could stick it in there. And that's essentially what our approach is for working our data grid with Storm. So We substitute disk-based queue for a reliable in-memory queue. So the spout, in other words, is instead of reading from a disk-based queue, reads from an in-memory based queue, in this case hosted in XAP. Could be some other in-memory source. We synchronously update the state in XAP here rather than Cassandra. So instead of having the limiting factor be the speed at which Cassandra can write, now the limiting factor is the speed at which XAP can write, which we have already discussed is 200, 300 microseconds, something like that. And then ZAP takes care, or the grid takes care of updating Cassandra asynchronously behind the scenes of everything that's going on, including, by the way, not just the original events, but anything else you'd want to persist in Cassandra as well. How are we doing? I think we're getting near the end here. So here's a sample architecture that's got everything under the sun in here. You can have Cassandra serving clients up here. We see Hector, SQL, Astyanax clients here. Not everything needs in-memory processing, right? So there's no reason to pretend that everything has to go through this architecture. So there's no reason why this might be 80, 90% of traffic goes through this. Who knows? Events and queries and streams can go into XAP. Alternatively, streams and queries can also go into Storm, because I didn't mention that Storm also will serve distributed remote procedure calls as well. But it doesn't provide persistence in memory like a data grid does. So the streams can enter into XAP. Those streams can feed Storm, do in-memory processing. The results of state and other events that you want to happen can go into XAPs to the data grid. The data grid can then actually use its eventing capability to notify external clients, any other listeners that are attached to whatever is occurring in memory. These queries up here going into the data grid can be, they're SQL-based sort of Hibernate-like queries that you can run on aggregators and objects in memory. And then asynchronously along this path, Cassandra, of course, winds up consuming everything in the end, everything you want it to. Let's see. Okay, so I've got some references for this. You can actually try this out if you're ambitious. We have a product called Cloudify, which will allow you to, I'll upload these on SlideShare as well. We have a Cloudify recipe that will start up everything for you, a complete Storm cluster along with an XAP-based cluster and some components in order to facilitate streaming. The source is available. The spout for XAP is there. It's a transactional spout. It's batch. It can replay batches, batch-oriented, and so forth. And more background on the effort. I've written a couple blog posts, and part 3 is coming soon. I'm a little bit behind on my blog posts, but basically how this whole thing was built and put together. So that's it. Thank you.